네, 안녕하십니까. 오늘 참석해주신 참석자분들께 감사드리고요. 저는 컨델라 코리아의 안도현입니다. 오늘 저번 3주 전에 진행했던 1주차 강의에 이어서 2주차 강의로 오늘은 패밀리 오브 폰토닉 퀀텀 알고리즘에 대해서 설명을 해주실 거고요. 컨델라 본사에서 어플리케이션 쪽 개발을 담당하시는 아르노 리코님께서 강의를 진행해 주시겠습니다. 네, 그러면은 아르노 리코님의 강의를 시작하도록 하겠습니다. Yeah, Arno, you can start, please.
Thank you very much, Doyun, for the introduction, and everyone, happy to see you again and that you followed all these classes. So my name is Arno Ricouga. I'm in charge of the application at Quandela. And today, as I believe Doyun explained, can you see my screen?
Yes, I can see your screen.
Okay, good. We're going to talk about quantum algorithm and Quandela toolbox. So before starting, let's highlight what are the goals of the lesson. So first, we're going to give an introduction to complexity classes. And then we're going to talk about the main categories of fault-tolerant algorithm. Moving on to noisy intermediate scale algorithm, so the algorithm we can implement today on the device that is that are available. And then we're going to talk about the Quandela toolbox of algorithm, which is a set of algorithms developed by Quandela's engineer that are really high level, so easy to use for even for people that don't specifically know about either quantum or photonic. So before talking about fault-tolerant algorithm or algorithm in general, one should bear in mind this definition of complexity classes and where does quantum computing fit into this complexity of real-world problem. We'll see that there are actually some state-of-the-art classical algorithm that will find it difficult to solve some everyday problem. So first of all, how one determines that a problem is hard. So to do that, we find an algorithm to solve it. It can be naive, like a brute force algorithm. And for this one, we will look at the problem size with the problem size and the memory usage. And as this grows, we look at the runtime analysis and the resource consumption of our algorithm. And this leads us to a set of really unknown complexity classes. One of them is the class P. So P stands for polynomial time. So it's a class of algorithm that can be solved deterministically and efficiently on a classical computer. What we mean by efficiently is polynomial with the input in polynomial time with the input of the problem. This class is also known as the class of problem we can solve efficiently, even though it's not strictly accurate. There are problems that are out of this P class that we can still tackle efficiently by approximation and so on. And this leads us to the class BPP, where in this case, we again try solving efficiently a problem, meaning in polynomial time, but we may have an algorithm that is probabilistic and find the solution only from time to time. And then one also of the really famous class is the NP class. NP stands for non-deterministic polynomial. So in this case, the polynomial refers to the time it requires to check a solution is a solution of this NP problem. I forgot to mention that these P and NP problem, they are decision problems. So problem you can answer with yes or no. NP problem are really, really interesting, especially for quantum computer, and I will explain why in the next plot. So the plot that is shown on the next slide. Then we have counting problems, so related to the P class, and we also have a problem that can be that we know cannot be solved in exponential terms. So again, really hard problem. And for these classes where we have known problems for each of them, for instance, tackling a Sudoku is like a general case Sudoku when the size of the instance increases is NP hard. Finding only one shortest path for a drone in the city, that's a P problem, that's polynomial time. But if you want to tackle a multi-agent path finding, so you have many drones that needs to find the shortest way in the city, for instance, with fixed starting point and destination, that's a NP hard problem as well. There are also many hard computational problems in drug design, molecular dynamics, because these are problems with the number of variables exploding with the number of atoms we take, for instance. In the aerospace industry, the gate scheduling problem, where we want to assign a plane to a gate when it lands, is also a complex problem in the NP class. There's also many complicated problems as well as polynomial problems in finance with time series forecasting and so on. And here I show the Venn diagram of complexity classes. So this is quite important to understand how each class is related to the other. So as I was saying, P problems are the easiest to solve, thus they're represented by the smaller circle. And then the hope and of quantum computing is that so BQP, which is the class of quantum algorithm, the class of problem quantum algorithm can solve efficiently. So it takes a polynomial amount of time to solve this problem on a quantum computer. Is believed to be greater than P and within NP and maybe a bit out of NP, which means that there may be hard decision problem, but that are easy to check, that belong to BQP and not to P. And that's exactly the kind of problem we're interested in. And that's the case, I mentioned it in the first session we had together, like offshore algorithm, to factor an integer in prime numbers. That's what we wrote here by factoring discrete log. It's the same algorithm we have in mind. Other instance of problem like in P space, you have the n times n chess problem. So that's the P space. For the NP class, you have the finding graph isomorphism, or even checking if graphs are isomorphic is an NP problem. Driving salesman problem is maybe one of the well-known NP complete problem. And then we also we have another instance of a P problem with graph connectivity. And so, as I was mentioning, how the quantum approach can help. So the class of quantum algorithm that can be solved efficiently, BQP, is believed that is greater than P and have algorithms such as Shor, VQE, QAOA could be in this class also. It still needs to be proven, but to solve satisfiability problem and so on. So that's it for the introduction about the complexity classes. There's much more to say about it, and there are great resources we can share with you if you're curious. Now we're going to talk about famous fault-tolerant quantum algorithm, and they can be described in 4 classes. So first, the algebraic and number theoretic algorithm, like Shor algorithm. Then oracular algorithm, like Grover's one, approximation and simulation algorithm, and then optimization numerics and machine learning algorithm. You can find many of these algorithms on the quantumalgorithmzoo.org. I strongly suggest to have a look at this website. It's sort of a review paper of quantum algorithm, but it's being, updated regularly, and that's why it's a really crucial resource to use as a quantum algorithm designer. So, for algebraic and number theoretic algorithm, we get speedups from polynomial to exponential for Shor algorithm, for instance, which is useful for quantum cryptanalysis. In our oracular algorithm, we have speedups varying to constant factor, which in some cases enough for some practical use case to get an advantage. To super polynomial, like Grover's algorithm. Another instance of problem that can be tackled using oracular algorithm are the abelian hidden subgroup. And the Joyce algorithm is one of them as well. I introduced it in the first class. It's about checking the priority of a function. Also, graph properties in the JCC matrix model is something that can be checked with oracular algorithm. Just to say a few more words about oracular algorithm, it's a kind of algorithm that they're based on an oracle. So that's a black box that will tell you that is able to mark down the answer of a given problem or not. And that's how all this problem works. Then we have a class of algorithm called approximation and solution algorithm, where we can get speedups from polynomial to super polynomial, and algorithms such as quantum simulation, QAOA, is one of those. It's an approximation to solve optimization problem. We also have simulated annealing in this category, and quantum semi-definite programming. Last category about optimization, numerics, and machine learning. So they are known machine learning algorithms that will provide a super polynomial speedup on the quantum machine. Most of them are applied to quantum data, which makes sense, faster to and better to learn quantum data on a quantum computer than on a classical one. And so you have a bunch of classification tasks, reinforcement learning, QBO problems about that. Again, to have more details about each algorithm paper related to that, I strongly should suggest to go on the quantumalgorithmzoo.org. And now the class of algorithm we are more focusing on these days, since they're the one we can have on the current hardwares, are the NISQ algorithm. The first example of that we actually implemented at Quandela is generation of random numbers. So we called it entropy. It's the first useful application of our 2-qubit QPU. Can be either useful for cybersecurity or Monte Carlo simulation. And it works as follows. We set a bunch of entangled qubits, and then we're gonna measure them and store the statistics, the correlation between all the measurements, and compute a value that we're gonna get compare to a threshold. And if the value go beyond the threshold, which is called like the Bell inequality, we know that we generated like random numbers. So that's a threshold that is quantum cryptographic secure. Like we know that if we go beyond this threshold, the random numbers have been securely generated. And it can be used for a lot of external application. I mentioned cybersecurity, Monte Carlo simulation. Can also be used for blockchain because you need secure random numbers in this one, Internet of the Things, data encryption, and so on. You can try this algorithm remotely or on-premise using our quantum computer. and the rate of generation is around, above 1 million random numbers per day. Another class of NISQ algorithm are variational quantum algorithm. So that's one of the most promising approach to prove like a practical quantum advantage in the NISQ era. So they're generally a general hybrid technique with a bunch of variational parameters that are being adopted in the problem that's being solved, and use classical optimization to solve the quantum circuit. A bit more concretely, the first step for designing such an algorithm is to have a cost function O that encodes the problem that needs to be solved. So this is represented on the scheme by f theta of x. And then we create a parameterized quantum circuit U with variable with a bunch of variables. Here they're represented by this blue box and are mathematically named theta. And then once we see that this function f depends of theta, we're gonna compute the loss function and minimize this objective with theta, which leads us to a new theta called theta prime that's gonna be updated in the circuits. And once we updated the parameter theta prime, we repeat the sequence again, meaning that we get some measurement, compute the function f of theta and the loss, and then do this again, this classical optimization step to have new parameter to update in the circuit. And we do that over and over again until we reach a threshold, so a convergence of our algorithm. So that's it for variational quantum algorithm. I will come back to them later, presenting the Quandela toolbox, because the majority of the algorithm we're running today are using this method. Then there is the quantum annealing algorithm, which is a process by which one optimizes a function for finding the global minimum using quantum fluctuation. So it's based on effect like the tunneling effect, for instance, and the adiabatic evolution in order to move an objective function around its landscape. So it's nicely shown on this plot here, where we may initially start with the top blue dot, but then if we correctly encode the problem into the Hamiltonian of the system, and then we lower the temperature of the system, then it's going to move little by little to the global solution using quantum tunneling and taking paths that are easier to take compared to classical paths. Another crucial model of doing quantum computation is boson sampling. So why it is super important, because it's the leading proposal to show a quantum advantage. And it's, so I believe you came across this several times now, but it's always good to have a reminder about it. It's a process which by which we sample from a distribution, probability distribution of single photons traveling through an interferometer. So we generate single photon, they go onto a chip, that's the chip, and they will interfere. Some of them will be in the same mode, some of them will be in two different modes. You can even have 4 of them in the same mode. And what you want to guess is where they will end up in the output of the circuit. That's given by the computation of the permanent, which is known to be a sharp P problem, which is a hard problem to solve exactly for a classical computer. But with a quantum computer, we have a straightforward way, and especially with our quantum computer, we have a straightforward way to do it and to compute this to sample from this probability distribution. Another class of, well, they're not quantum algorithm, but they're inspired by quantum. It's tensor networks algorithm. They are currently the most sophisticated classical way of simulating quantum computing efficiently. And they combine like techniques from AI taking inspiration for quantum. So how does it work? We first obtain a quantum state representation. So you know now that a quantum state has like exponentially many possibility compared to, so if you take an n qubit state or n bit state, you have 2 to the power of n possibility for the n qubit space. And that's hard to represent classically. So what we do is instead of having this state in just like a big tensor of dimension n, and when we represent this quantum state in smaller tensors, as shown here, and so on the right you have the quantum circuit, on the left you have the tensor representation of this one. And this requires much less. So we do some assumption. We just take into account the more like the strongest entanglement between parties. We don't look at like the full description of the states, but that allows us to have and to simulate much bigger instances of quantum state and to mimic some operation of a quantum circuit. For instance, like the company Multiverse Computing recently claimed that they're able to mimic the quantum computer IBM announced this Monday of 1,000 qubits using this kind of approach. So each of these class of algorithm, and to sum up, have pros and cons. So for variational algorithm, we have low circuit depths in combination with classical technique that make it suited for near-term devices. Unlike FTQC algorithm, where you need like a huge depth, which means that you need quantum, you need qubit that stays in the state for a really, really long time. They need to have a really long coherence time. Then the cons of the variational algorithm is that we can only handle algorithm with a limited number of qubits due to the current noise, and the fact that we have small circuit size and small depths of circuit means that you can also only tackle small instance of problems. Then we have quantum annealing. So this approach, one of the main advantages of this approach is that it can potentially find the global minimum of a cost function much faster and more reliably than a classical computer. But first, you need to map a problem into the cost function of an Ising model, which is not universal. Like you can only do it for certain kind of problem. And it requires some work to reformulate given problems to fit this format. Also, this approach has been around for quite a long time with machines from D-Wave since the year 2000. And I mean, we haven't seen an algorithm giving a quantum advantage, like boson sampling, for instance, where it's been shown that using boson sampling, you can have a quantum advantage. For now, it's an ad hoc algorithm. It's not useful for any practical problem, but we know that some tasks are harder to tackle on this device, easier to tackle on this device than on a quantum computer. And as I was mentioning, is the leading quantum advantage proposal. What's limiting in this approach is that the amount of photon you can get is restricted because we have a lot of photon loss, and we are lowering it as much as possible. And then it's not an approach where you can scalably encode qubits using photons. So as a recap of quantum algorithm, so the goal is with quantum algorithm is to tackle problems that classically they cannot be solved efficiently. We have a bunch of quantum options to do that. So many class of fault-tolerant quantum computing algorithm, which will require like hundreds of thousands of qubits to be run for like interesting instances. Then we have some algorithms that belong to FTQC that we try to adapt to NISQ, but also algorithms that are strictly NISQ that we presented. And we explain also the importance of the hardware with the algorithm. So for instance, some hardware would be better suited for annealing problem, other for Boson sampling. What's coming next is the Quandela quantum toolbox. So in this one, we're going to talk about the machine learning algorithm we implemented, and more specifically, the quantum machine learning algorithm we implemented. I'm going to talk about a variational quantum eigensolver as well. The strategies to enhance the performances of those. And then what we also have QBO problems, so quadratic and constraint binary optimization, as well as graph algorithm in the quantum toolbox. So the first release of the toolbox is planned before the end of the year, and then we continuously improve it and let you know via Medium posts and LinkedIn posts of the newcomers, the new algorithm that are running. So that's the toolbox. As I was mentioning, so we have a bunch of VQE algorithm. We have algorithm for generation of random numbers that I introduced previously in the NISQ category of algorithm. QBO algorithm for quadratic and constraint binary optimization problem. Graph problem, which it's a really nice one because it's native photonic and it can check if two graphs are isomorphic. Remember that we mentioned this at the beginning with the complexity classes. We can also find dense subgraph of a graph and the number of perfect matchings. Don't worry, I will remind what a dense subgraph is and what are perfect matchings later in the presentation. And then there's a bunch of quantum machine learning algorithms that use, well, you can see quantum machine learning like a synonym of a variational algorithm. And in this one, we are using native photonics algorithm. So the idea of the toolbox and why it's interesting for our users and even for you if you'd like to play with it is that each of these toolbox and algorithm, the toolbox will unlock tens of different use cases. For instance, VQE, you can find the lowest energy of a molecule, but you can also solve optimization problem, and this applies to quantum chemistry, to combinatorial problem like in logistics and so on. For entropy, for generation of random numbers, you can use it for encryption of data, you can use it for Monte Carlo simulation, and that's just a few ideas. You can have many, many more applications for this one. QBO problem, you can find such problems in, as I was mentioning, logistics. For instance, the knapsack problem can be mapped into a QBO problem. There's also a way to find shortest path and a bunch of shortest paths using a QBO approach. Also, train unit assignment problem is a famous problem in the railway system that we can target with QBO. Or in this one, we showed like finding the optimizing portfolio in finance. About graph problems, we can use them like finding denser subgraph can be useful to detect fraud, as fraudulent agents are densely connected on transactions graph. It's also useful for loan matching, where you need to know many-to-many match to one-to-one match. That can be we can again use like this graph algorithm we present. And again, quantum machine learning, it would be as ubiquitous as machine learning, and presenting clustering to cluster data, for instance, useful for fraud detection, or to for risk-adjusted portfolio optimization, again with clustering. But you can think of prediction of many of different molecules for material design and so on. So these algorithms, the toolbox, will unlock tens of use cases, and we make them easy to use for Quandela users. Let's deep dive now into entropy, the quantum random number generator algorithm. So what we propose in this algorithm is a quantum advantage for non-local games. So what's a non-local game? I will remind it here. So you assume that you have two parties, Alice and Bob, separated, physically separated. They cannot communicate with the other, and they've been asked question 1 or 2. So question 1 or question 2, and we look at the answer, whether it's answer 1 or answer 2. If they share a classical strategy, the accuracy of the answer, so to win this game, cannot be higher than 75%. But if they share some quantum resources, so Alice and Bob are some superhero having some quantum power. Well, if they share entangled strategy, meaning an entangled state, they can go up to 85%. So we see that we can go beyond classical strategy. And if we know that we are beyond that, and we have this advantage, well, it is known that the answers Alice and Bob give cannot be known in advance. That it's a mathematical theorem that tells us that. And this is why we use that. We implemented on the chip where Alice and Bob are represented by modes. So Alice is 1 qubit, Bob is another one. And each of the answer they're going to give will give us random numbers, or random numbers to then use for cryptography in Monte Carlo and so on. Another set of algorithm I did not mention because it's still like not mature enough to go in the toolbox yet, but will soon go. So it will be in the toolbox in 2024. It's the reinforcement learning class of algorithm, where we use what we call quantum photonic projective simulation. It's a kind of reinforcement learning framework. So for those who are not familiar with that, reinforcement learning is about an agent with an environment, and the agent is trying to learning a causal model of this from its interaction with the environment. So the environment will tell him some information, some state. He will guess an action to have and send it back to the environment, and will receive a reward about that or not. You can think of that as a robot trying to play chess and learning how to play chess. And we use this framework to, for instance, identify which of these objects are red squares. And we show that with quantum projective simulation, we have an advantage compared to classical projective simulation. Like we can reach 100% accuracy with quantum projective simulation, but we cannot do it with classical projective simulation. And as this model is versatile, we applied it to different problems such as grid path finding. So for a drone to find its path on the grid. We also have in the toolbox a QUBO algorithm, where the goal is to find the solution of a quadratic function, where the solution is represented by a sequence of binary variables, B. The matrix of the problem is defined by Q, so this M by M matrix. And what we do is minimizing B, QB, so it's quadratic, meaning because we have 2 B's multiplying. and we finding the minimum of B of this scalar product. And we applied it to a bunch of problems, and it's efficiently working for trap problem, or what I call trap problem is train unit assignment, where we try to assign train unit to given trips in a timetable of trains. So we applied it in this case, and it works fine. Another algorithm we are heavily investigating in the application team at Quandela is the variational quantum eigensolver. So that's a must-know algorithm in the NISQ era. It's about finding the ground state energy of a molecule, giving its coordinates, the coordinate of its nuclei. And it's a kind of variational algorithm, so we will have this back and forth between the classical processor, optimizing over a set of parameters defined on the quantum circuit, and then trying to reach an optimal solution. So as mentioned, in the toolbox, we have an example for the H2 molecule, and soon we're gonna have example about lithium hydride, H2O, or even barium hydride. And how it works is that we prepare an NZAT, or you can think NZAT is a synonym of a quantum circuit. And then this quantum circuit has some variational parameters. We convert the chemical problem into a qubit Hamiltonian. And whenever we do measurement on the circuit, we measure in different bases and compute the qubit Hamiltonian of the problem. That would give us an approximation of the ground state. And then using the variational principle, we know that if we minimize this function, and we find the global optimum would be the ground state of the molecule. So we do that and we repeat the process again with the back and forth with the classical algorithm to reach a threshold. And that's the kind of plot we obtain for the H2 molecule, where each dot that you see is the energy, the minimum energy in R3 for a given bond length in angstrom. And again, this VQ algorithm can be extensively used in different setup, on different problems. So we applied it to structural mechanics problem, where the problem was the following, where we had a 2D mechanical structure and we had a crack in the dam, and we wanted to know how this crack is going to evolve with some tensors constraints on this dam. So what we did is, instead of solving it with finite element method, what we do classically, so finite element method is putting a mesh on this 2D structure. So we have, and solving the differential equation on discrete point of this dam, of this 2D structure. Instead, we found the an energetic formulation of this problem, where so it's written like here, and then we minimize this energy with a variational algorithm. So it's like a VQE, where you want to find the ground state of this molecule, and giving the ground state of this molecule will give you the solution of this problem, meaning how the crack will evolve with time and with this constraint. So it's again a hybrid algorithm we use, and we really happy about this one, because we show that for the specific cases, it's quite well, it scales well, meaning that, for instance, the rigidity matrix is a simple tensor product of operators, so that's easy to embed in the quantum computer. It's easy to prepare the state F and psi that are used for to find this, to compute this minimum energy. And we only need a few amount of measurements to have the information around the crack we are interested. And so that makes it a really promising algorithm to beat a classical algorithm in the NISQ era. So it may be in the coming years. So yeah. Stay tuned about this one. We are preparing a paper with more information. So if you're curious about it, we're soon going to publish something on the archive. And we also have like a generic VQE algorithm where we have an ansatz that is general and can be scaled to 14 qubits in simulation or 4 on Haskella. And it can be used to, well, tackle the problem you may think of. So if you have a problem that is about solving the minimum energy, I strongly invite you to try this generic VQE algorithm that is in the toolbox and to tackle this problem. We also use VQE and variant of VQE called CVAR VQE, conditional value at risk VQE, to tackle optimization problem, and in this case, optimizing QUBO problem. In short, what CVAR is about is instead of taking, in the Hamiltonian, you have a bunch of expectation value that you want to compute in the variational quantum eigensolver. In this case, we just keep some of these expectation value, and we're just going to keep the one that are the most relevant one. And that's interesting because it allows us to have a resilient noise generic algorithm using VQE, because we get rid of like these little noisy terms. We just keep like the most important one. And it's, well, building on our knowledge of VQE, and it has and it behaves faster than QUBO on this for these problems. And to give you an intuition, so this CVAR VQE depends on this parameter alpha, which is the number of elements you want to keep in the full distribution. So if alpha is equal to 1, we run the full VQE problem. But if we take an alpha smaller to 1, we just take the segment of probability distribution. And we see that here, by taking alpha between 0.1 and 0.25, we get quicker convergence compared to taking an alpha equaling to 1. A super interesting algorithm that we developed is the one to tackle a graph problem. So what's interesting is this one is that we managed to link the problem of boson sampling to solving some graph problems. So how did we do that? We encode matrices on a universal interferometer. Then using single photon, we are able to compute some values about the graph that is represented by these matrices. So the process goes as follows. We take a matrix A that represents the adjacency matrix of a graph. So whenever two nodes are linked, so if node I is linked to node J, we put a 1 in the ij position of the matrix. That's how we define the adjacency matrix. And then we scale this matrix down so that all the values are, between in a good segment. And we dilate this matrix into a unitary one, because there's no reason this matrix is unitary, and we need unitary matrix to implement it on our quantum computer. So we put this matrix AS in a bigger one, and we know that this bigger matrix is unitary, so we can then encode it onto our universal interferometer. And then we're just interested in the information about AS. So we're going to put photon in the first mode corresponding to these rows and columns, and looking at the case where we detect photon only in the upper modes corresponding again to AS. So what we're going to compute is the permanent of this matrix AS, which is super interesting to, as I think I show on the next slide, for different problems that I would explicit later on. And that's a snippet of the code where we define a unitary from a matrix A. So we have this matrix A. I know you have a Perceval class, but I give you some hint of how we do it here. So given this adjacency matrix, so we compute it starting from this network X graph. So it's a way of representing graph in Python. And then we're able to dilate it, and then we return back this dilated matrix. So that's what I just told you about. And for instance, we solved it. So sorry, we applied it on this graph to find the densest subgraph of this one. So it's quite easy to see that if you're looking at three dense subgraph of size 3, of this graph, they are located here. So it's 2, 5, 4, and 3, 5, 3, 4, 5. And we see that giving the proper seed, so either if we give seed 2 or 4, we manage to find this using this algorithm. And then we also can apply it to checking if two graphs are isomorphic. And this works, well, I won't go into the details of this one, but I strongly suggest you read the paper if you're interested in this one. So the paper is not a graph problem with single photon, and it's well written, and you will have much more information than on this slide. So what are the key takeaways from this lesson? So that there's strong reason to believe that there are hard problems that classical computer cannot solve that quantum computer can. And we solve them using quantum algorithm that I show you that we separated in fault tolerant algorithm. So one that will be implementable on a quantum machine that requires hundreds of thousands of qubits. And we talked about like these main algorithms again, so Grover, Shor, and the class like oracular algorithm, cryptanalytic algorithm, and their respective quantum speedups. And then we talked about the NISQ algorithm, so boson sampling. It's a NISQ way of doing quantum computation. Variational algorithm, generating random numbers is also a NISQ algorithm. Quantum annealing, which is the last one we talked about. And we talked about the Quandela toolbox, where we have a bunch of high-level algorithms, easy to use, where you don't necessarily need to go deep down into quantum algorithm, but you can use them to tackle tens of use cases. Thank you for your attention. I think we have some time for questions, so please feel free to send them into the chat, and we'll answer them as they come.
네, 질문 있으신 분들은 지난주 강의와 동일하게 그 채트로 남겨주셔도 되고요. 아니면 마이크 켜고 질문해 주셔도 됩니다. 질문 부탁드립니다.
Everything seems to have been very clear. Waiting for potential question, I would like to add that the algorithm that Arno presented, so there will be a second part of this training session just after the new year, when we will interactively show how it works concretely and make some development with Perceval, which is a framework that we have to develop quantum algorithm and photonic quantum processor. And the goal of this session will be to help you to implement such algorithm, to see how they apply to a concrete problem, and to so that you can get familiar to development of such algorithm for photonic quantum computer. So this will be interactive session where we will We'll first show you how Perceval is working, the different concepts, and then we will step by step we will implement some of these algorithms, and we'll go through the complete implementation.
So I
There's
think
a
we
question.
I think we have a question popping in. So you're welcome. My pleasure for the presentation. So the first one is about the differentiation of how do you differentiate a single photon into an interferometer? Do you use a variable focus lens with AOD? So in the class that Nicola gave, I think he showed how, and I think this will also be highlighted by Pascal in the class she will give tomorrow, but we have single photon source and that generate single photon, and then we make them travel through optical fibers, and that's how we send them into the chip. So you asking if we focus them with the AOD. To be honest, I don't know what an AOD is. It's maybe an acoustic optic deflector. If it's that, maybe Jean, you have a better view than me on this problem. So I'm doing mostly algorithm, not expert in experimental details, to be honest.
Yeah, I don't understand on my side what you call by indifferentiate a single photon, but indeed we are using AOM, not EOD, but to route photons inside the photonic chip. And the point is not to have only one photon, it's to route a set of photons, a collection of photons. So there is a process. You can look at the presentation from Nicolas Marin, where he was showing the complete demultiplexing. We call that the demultiplexing process to prepare the photon, the single photons, to enter the photonic chip where they will be interfering at the end. And I'm continuing on the second question part, where you say, yes, the main problem, and it's one of the things that we mentioned, is that the photon can vanish, can be absorbed by any solid particle that it encountered on its way. And in that case, the process depends on the algorithm. There is some algorithms that are robust to photon loss. It is what you call the photon loss. And there are some algorithms that require that you have at the output the number of photons that you send in the input. In that case, we simply discard the result and wait for the next one that will have the correct number of photons. So it is a bit it could like a bit strange that we just discard some output, but we need to keep in mind that we have generating photon at 80 megahertz rate. That means that losing some of the sample is not a big deal for most of the algorithm. We are still far faster than any other quantum computing platform that's run at millihertz or microhertz, a millisecond or microsecond rate. So here we are talking about nanosecond. And yes, definitely the main issue in this area is the vanishing of the photon. It is what is in the presentation of Nicolas Marin. To improve and to go to larger number of qubits, we need absolutely to improve the transmission of the system progressively so that we can work with more photons.
Then we have another question from Eun-Young Cho about the communication between the classical computer and the quantum one, if that's a problem. So I'm not really sure what you think of, but first of all, we know really well. I mean, you know, we talk about a quantum computer, but as we mentioned in the first class, it's more quantum processing unit, so it's always communicating with a classical device, and it needs to be embedded into a classical setup. Yes, and I see that your worry is about room temperature. So we manipulate photons that are, well, they don't need to be processed at low temperature. They're manipulated at room temperature. So the electronics to interact with the photons is at room temperature, so that's not a challenge for us.
The only need of the low temperature is for the input set preparation, but
Yes.
there is no computing done at low temperature. Indeed, it would be a major issue, and at some point it will be critical to have operation at low temperature to improve latency, to have some fast, what you call fast switching in a photonic circuit. But this is not, it's something that we'll tackle in few years probably.
And the second part of the question is about quantum machine learning or reinforcement learning, if we can use it for quantum, well, I would generalize the question to quantum error correction. So there are people studying that. It's more so, myself, I'm more working on the application side. And what I mean by that is like industrial cases, like real industrial problem or problem in insurance, banks and so on. Not that much in quantum error correction, but I know that people use reinforcement learning and machine learning with that. The best, if you present tomorrow, and well, it's not too much related to what Rawad Mezer is going to talk about tomorrow in his class, but it will be the kind of person that knows more about this kind of method. No problem. Thanks to you for the question.
Okay, I think we don't have more questions. So I would like to mention that tomorrow we'll have two presentations, one on the physics on quantum dots by Professor Sonella, and it will be followed by benchmarking. Benchmarking is a key notion in quantum system because it's quite hard to systems are not perfect. It's not like classical computing where you know that when you have one processor, then you can say, okay, this makes this operation. So we need to know exactly how good is a qubit, what we can do with quantum processor. And there is a lot of studies on benchmarking, how to compare two systems. How do you compare ion trap with a superconducting quantum computing system, for instance, or photonic system? And Rawad Mezer will talk about all this, the problematic behind the benchmarking. In classical world, do you know that there are some benchmark on operation per second that is called FLOP, floating operation per second? This type of benchmarking doesn't apply for quantum computing. So we need to find some way to be able to evaluate the quality of a quantum processor.
네, 그럼 더 이상 질문이 없으면은 오늘 강의는 여기서 마무리 짓고요. 내일 이제 되게 강의가 좋은 강의들이 또 이어서 있으니까 내일 3시에도 많은 참석 부탁드리고요. 오늘 참석해 주신 분들도 감사드립니다. 네, Arno and John, thank you for your time and thank you for your questions and answers, and thank you for your time. Thank you very much.
Thanks, everyone.
Thank you.
Bye-bye.
Thank you. See you soon. Bye.